To the video on Gay-Lussac's law from Chapter 6, Section 5. Gay-Lussac's law has a relationship between temperature and pressure. In Gay-Lussac's law, it says that the pressure exerted by a gas is directly proportional to or directly related to the Kelvin temperature. And so if temperature increases, pressure increases. If temperature decreases, then the pressure of a gas will decrease as well. And so we can write this mathematical expression, assuming that the volume and N, which is the number of moles of a gas, are constant. So we could say that P1 over T1 equals P2 over T2. Okay, this diagram here is just representing that if you increase temperature, that you also are increasing the pressure. So we want to solve for one of the variables. We have to use algebra to rearrange the equation. And so depending on what you're solving for, so here if we were solving for P2, we would have to rearrange the equation. So basically multiply each side by P2 and bring it to the left side to isolate our P2 by itself. And so we would have P2 is equal to P1 times T2 over T1. Okay, so here's our T1, so we would divide through still by it. We would just bring our T2 over to the other side. So we look at an example of how to use Gay-Lussac's law. If a gas has a pressure at 2 atm and 18 degrees C, what is the new pressure when the temperature is 62 degrees C? Okay, since we're looking at the difference in temperature and pressure, we know that we're going to use Gay-Lussac's law. And we should also know, just by the time we get to the end of the problem, it should make sense. If our temperature is going to increase, which it is, our temperature is increasing to 62 degrees from 18 degrees C, then we know that if temperature increases, then pressure also increases. So we should see an increase in pressure. If we do not, then we know that we've done something wrong in the calculation. So here we have P1 is 2. So if we write out all of our data so we can organize it to fit it into the equation, then P2 is what we're trying to find. T1 is 18 degrees C. And we know that for gas laws we have to change to Kelvin. So we would add 273 to 18 to give us 291 K. For T2, we'd have 62 degrees C plus 273, so 335 K would be our T2. If we rearrange to solve for P2, just as we've shown before, where we moved T2 to the other side to isolate P2 by itself, and we have our equation, and then all we have to do now is plug in the values. And we have 2 atm is what we started with, which is our P1, and we have 335 for T2, so be sure you notice that T2 is on top, T1 is on the bottom, and then we have 291 K. Our kelvins cancel, so our units there cancel out, and we are left with 2 times 335, or 2 times whatever you get for 335 divided by 291, and that gives us 2.3 atm. Here's another example that you can work, and then you can pause the video if you'd like, and then we'll show the solution. But we have a gas with a pressure of 645 torr at 128 degrees C, and we want to know what the temperature is, so what T2 is in Celsius if the pressure increases. So we're having an increase in pressure, and so we also know that we should have an increase in temperature. Okay, so we organize our data. P1 is 645 torr. Okay, we can use torr or atms. And we have 128 degrees C plus 273. We have to change from Celsius to Kelvin. And we have 824 torr, and we are finding T2. So whatever our Kelvin minus 273 would give us degrees C. Okay, so if we plug in, and first we have to rearrange and solve for T2. Okay, so we're going to isolate T2 by itself. So we're going to move Either way you want to look at this, you can look at it as moving your T2 over here, then having to rearrange and multiply through by the T1 on the other side. But when you rearrange and do the algebraic, you get T2 is equal to T1 times P2 over P1. So if we plug in the values, we have 401 Kelvin, and we have 824 divided by 645. That's our pressure ratio, which we know that's going to, our units cancel there. So we have 401 times whatever the number we get here when we divide these two numbers, and we get 512 K. So we see that we do have an increase in temperature, just like we expected. And if you subtract out, if you want to know the temperature in Celsius, now we just have to subtract from 273 or subtract 273 from 512 because we know that in gas laws we have to have Kelvin. So in order to get back to Celsius, we have to subtract 273. So we have 239 degrees C. While we are discussing temperature and pressure, there is a concept that we've briefly gone over through the videos and discussions, but about boiling point. I think even on your lab you all had to define what the boiling point is. What has to do with vapor pressure, and this is the pressure that accumulates when molecules of a liquid collect over the surface of a liquid in a closed container. And so when you think about the boiling of water, those molecules are accumulating on the surface of that liquid. And it's specific for a given temperature, and it increases when the temperature increases. And this makes sense since Gay-Lussac's law says that if temperature increases, pressure increases as well. And so when the vapor pressure of a liquid, think about your water that you're standing there waiting for it to boil, when the pressure of that liquid equals the external pressure, so this would be the atmospheric pressure of your home or outside or wherever that you may be, then the liquid reaches its boiling point when the pressure of the liquid equals the external pressure. Okay, and so if we look at the vapor pressure of water, and we know that 760, so if you look way down here at the bottom, we know that the boiling point of water is 100 degrees. And that matches up with when the vapor pressure is going to be 760 millimeters mercury or torr, or 1 atm. And in most of your, especially around in the south, the vapor pressure, or the pressure, the atmospheric pressure is 1. However, a typical atmospheric pressure in, say, Denver, Colorado is 634 millimeters mercury. And this means that it takes a lower temperature for water to boil. So at higher altitudes, the atmospheric pressures are lower, and the boiling point of water is lower than 100 degrees C. And so this is why you often see that people will cook food using a pressure cooker to obtain the high temperatures when they're trying to prepare food. So at different altitudes, the vapor pressure is different. So if you're up higher elevation, then your pressure it decreases. Therefore, the temperature at which water boils will also decrease. This concludes the video on Gay-Lussac's law.